Proof of property 1, associativity. So A times the product BC is the same as the product of A and B with C. So assume that A is an n times m, B is an m times p, and C is a p times q matrix, so that the above products are all well defined. So in particular A times B and B times C, well, the inner dimensions of the products of the matrices in these products are the same. For instance, B times C, here we have P, there we have P. Now we're going to write the ijth element in the product AB, and we use the sum formula, which is the sum of k is 1 to n of ai k b kj and bc. The element st in this matrix is the same as the sum of L is 1 to P, the inner dimensions, the number of columns in C, the number of rows in B, of B as L times CLT. So the ijth element in A times B times C now equals, well, first we use the same kind of formula. Instead of BKJ, we use BC and KJ. And then we use the second formula here. We just substitute K for S and J for T in this formula. And we get this one. It equals the sum K is 1 to NAIK, and we can move this sum out or write AIK to the inner part, and then we get this product of terms here. So now we can switch the terms, switch the sum sign, so we get the other sum now, L is 1 to P. And then we may regroup these elements over here, because AIKBKL is just the sum over here is just the ILth element in AB times CLJ. L is 1 to P, which is just the ijth element in AB times A times B times C. Proof of the associativity of the matrix multiplication. So the order in which we multiply in 3 consecutive matrices does not matter. So suppose we have an n times m matrix A, an m times p matrix B, and C is a p times q matrix. That means that all products that we have here are well defined. So A times B and B times C, and also the products over here, when BC is defined and A times BC is also defined, etc. You may check this by considering the inner dimensions of the matrices in a product. Well, then what happens? If we look at the element, for instance, if we look at the left-hand side, the matrix A times the product of B and C at row I and column J, well, by definition, this is no more than summing over the inner dimensions. K is 1 to m, A has m columns, times the kjth element in BC. And again, we're going to split off this BC. We're going to write BC kj as a sum. use the inner running variable L is 1 to P, the number of columns in B, which equals CLJ. So if we look more carefully at this sum, then this AIK does not interfere with the sum here, so we can get this sum on the left. Or another way of seeing this is remove AIK to the right hand side of the summation. So now we have an unordered triplet of constants, and we just may switch the summation signs. And now we take AIK and BKL together. And we slowly see that here we get an element of the matrix A times B. Yeah, because this is the element. Yeah, so we take this in blue. This is the element in the matrix AB on row I and column L. So this is AB and IL times CLJ, and again we use the matrix product form, so this is no more than the matrix A times B times C on the ith row and the jth column. So now we've shown that actually we have two matrices of the same dimensions with just the same elements in on the different entries in the matrix. So these matrices must be the same. So this shows one.